So, good morning, good afternoon, everybody. We're going to discuss today Chapter 10. Um Chapter 10 is about gases. It's in Chapter 10. We'll study in this chapter the physical properties of gases, and we are exploring how we can understand the properties in terms of the gas molecules. If you noticed in chapter 8 and 9, we discussed about geometry of the molecules pretty much, and we discussed about the VSEPR model. Chapter 11 is mainly about solids and liquids, so you can see how the chapters are coming along to each other in a very coordinated ways. In many ways, gases are more easily understood form of matter, even though chemically different gases behave different, but physically they are pretty much similar. A good example to take this into consideration would be air. As you know, air has oxygen and nitrogen, and oxygen has 21% about, and nitrogen has 78%. But if you see about the physical properties, they behave similarly. Oxygen and nitrogen chemically they are different, but physically they behave the same way. One of the things about gases that there are some gases we can call them monoatomic gases, like noble gases like helium, neon, xenon, krypton. These are monoatomic gases. We also have something called diatomic gases. A good example would be these are monoatomic, and a diatomic would be like something like nitrogen or hydrogen and oxygen. These are called diatomic gases. So there are also molecules considered as gases. Hydrogen cyanide is very toxic, but it's a gas. Or you can have hydrogen sulfide. It's also a gas. It's a toxic. Also has some kind of rotten egg smell. We have carbon dioxide. We have it's colorless and odorless. We have CH4. It's a colorless gas, CH4, but it's a flammable gas. We also have something called nitrogen dioxide, a brownish pungent smell gases. So these can be considered as some example of gases. So we have something called a homogeneous mixture. A homogeneous mixture is that it's a mixture. If you have two or more liquids or more solids, maybe in the form of homogeneous, that means you can't see any layer. Air is a good example. Air has oxygen and nitrogen together. Of course, there are some trace elements or carbon dioxide a little bit, but all these can be considered as a homogeneous mixtures. Now we're going to see about what are the properties that will define the state of a gas sample. So the most measured properties of gases would be its temperature, pressure, volume, and the amount of gas. These are the four variables that would help us to understand the property of gases. So in order to study the properties, we need to consider the temperature, the pressure, the volume, and the amount of gases. The amount of gases can be abbreviated as N. N refers to as amount in chemistry would be defined as the number of moles. I would say number of moles. So you have N. Let me write down here N for you. So these are the four properties that will pretty much define the state of the gas sample. So one of the measured property of gas is a pressure. How do you define a pressure? A pressure is a force that acts in a given area. So if I can abbreviate it for you, I will use F divided by A, where F stands for force that are applied in a particular area. So if you imagine a column of area with a 1 meter square cross section, let's say if you have a 1 meter square cross section, experiments show that it has a mass of 10 to the power of 4 kilograms. So if you just consider about the atmosphere, and if you cut the cross section of the atmosphere in a 1 meter square, that the downward gravitation force exerted on the column is about 10 to the power of 4 kilograms. This is not a random number, this is an experimentally determined number. So if you like to measure the force that exerted on this column, is going to be mass times area, which is 10 to the power of 4 kilogram, times the gravitational attraction. A downward attraction would be 9.8 meter per second square. So approximately that would give you about 1 times 10 to the power of 5 kilogram meter per second square. So the standard unit for kilogram meter per second square, the SI unit, is Newton. So we use 1 times 10 to the power of 5 Newton. So the Newton is the SI unit for force. So the pressure exerted by the column is the force divided by the cross-section area, which is 1 meter square, which means that we have 10 to the power of 5 Newton over 1 meter square. That would give us about 10 to the power of 5 Pascal. Now remember, Pascal is the name of the scientist who actually developed or calculated the how much force would be exerted in 1 meter square, which is if you consider the atmosphere in a cross-sectional area, the gravitational attraction is about 10 to the power of 5 Newton over 1 meter square. So in remembering his name, they use the abbreviation Pascal. So there are also other units of pressure, but Pascal is one of the common units. 10 to the power of 5 Pascal can be rewrite as using some of the prefixes. You can say 10 to the power of 3 kilopascal. That's one way you can write, or you can also say that it's like 100 kilopascal as well. I mean, both are, this is just terminology, you can use the different prefixes. So 10 to the power of 5 Pascal is the atmospheric pressure. It's considered as atmospheric pressure that is calculated at sea level. Okay, it's calculated atmospheric pressure calculated at sea level. You know, one of the things about pressure is that as you go up to high, the pressure is going to be different, it's going to be decreased. There, like I say, there are also other units besides Pascal. We use something called bar, B-A-R. It's also, we need to be familiar with this unit. Bar can be written as 1 bar. It's the same as 10 to the power of 5 Pascal, and it's also the same as 100 kilopascal. We also use a terminology millimeter of mercury, mm, millimeter of mercury. That's also another experiment done by a different scientist, that particularly these units are literally the difference in the heights measured in millimeter of 2 connected column of mercury. There is a picture in your textbook, you can look at it. There is a test tube like this. It's opened here, but it's sealed here. There was a plate here filled with mercury. The idea is that there is a pressure exerted on the on the top level of mercury, and since this is open, the mercury will rise up and it reaches to at a level of 760 millimeter. And assuming that this test tube is empty, nothing gas in it, sometimes it's considered as a vacuum, and it cannot be exceeding over 760 millimeter. So because of that reason, 1 atmospheric pressure, 1 atm, can able to carry or can able to deliver the mercury up to the length of 760 millimeter, and that's the reason that we can say 1 atmospheric pressure equals to 760 millimeter of mercury, which is equals to 760 torr at the same time, okay, which is equal to 100 kilopascal. Okay, all these units are used to express 1 atmospheric pressure at sea level. Okay, this is all these values are working at sea level, and these are considered as a standard pressure. So basically, a standard pressure, I would like to define what standard pressure means. Standard pressure is a normal atmospheric pressure at sea level. That's referred as a standard atmospheric pressure, which is equals to 1.00 atm. atm stands for atmospheric pressure, which is the same as 760 torr, or the same as 760 millimeter of mercury. Everything's at sea level, and which is the same as 1 times 10 to the power of 5 pascal, or you can say 100 kilopascal. They all are the same. Sometimes we may practice to convert atmospheric pressure to torr or to kilopascal. For example, I can give you an example here. Convert, let's do a little bit calculation here. If you have 0.357 atm, and if I ask you to change into torr, alright, so what we have to do is that we have to bring 0.357 atm, and if you like to change into torr, we need to basically put 760 torr over 1 atm. So we multiply 0.57 atm times 760 torr, and you know that the unwanted units will be eliminated, and we will have 0.357 times 760 torr. Most likely it gives you about 271 torr. So this is some of the examples that we can do. Let's say if you want to change 6.6 torr to atmospheric pressure, to atm. Again, 1 atm equals to 760 torr. So this can be used as a conversion factor. So we can say 6.6 torr times 1 atm over 760 torr. Torr is another unit for pressure, so we eliminate the unwanted unit and we divide 6.6 by 760, which give us we divide 6.6 by 760, which probably would give us, yeah, something like 0.009 atm. If you like, you can write this as scientific notation, which is be 9 times 10 to the power of 123, which would be like 10 to the power of minus 3 atm. Remember, units are very important. Now, this is how you can make a practice. You can switch numbers, and you know, in the conversion factor, one of the secret in conversion factor, always the desired unit has to be on the top and the unwanted unit has to be on the bottom. So that way you can eliminate the units, the unwanted units at the same time, and the desired unit will remain. So that way you know that you are in the right track. Now next we're going to see about the different laws. We're going to see about the Boyle's law, Charles' law, and Avogadro's law. So Boyle's law, let me start with Boyle's law. Boyle's law, what he tells us that he compared the volume of a fixed quantity of a gas at a constant temperature with pressure. So he compared volume versus pressure. Now when he compared volume versus pressure, what that he did was that he kept the temperature constant. Temperature is constant, and also the number of moles of a gas, which is N. N refers to number of moles of a gas, is constant. And one of the experiments that he did was with a J-tube shape, J-tube test tube. I'm not doing a good picture here, but what it says that a J-tube shape shown in the picture here can be a good illustration for a Boyle's law, which shows you that, let's say, you have the atmospheric pressure. Let's start with normal atmospheric pressure, 760 millimeter. You have a volume of about, I would say, 60 milliliter. Okay, so the idea is that if you increase the pressure, instead of 760 millimeter, maybe like you can make twice of 760 millimeter. So instead of 60 milliliter of volume, this is a pressure here. So adding the pressure is decreasing the volume. So you may have, if you multiply 760 by 2, maybe like I'm going to make another U-shaped tube. This time I will make a good one. But this time the pressure is going to be about 1520 atm. And Boyle stated that instead of 60 milliliter, you will have 30 milliliter. It's reduced by half. You see, you double the pressure. You make it twice. But the volume is like half. So what does that mean? It means that volume is inversely proportional to pressure. So this can be kept as a constant. So in other words, from this we can able to deduce it that volume times pressure is always gives you a constant. This is called a Boyle's law. So in other words, to summarize this, you double up the pressure, the volume is going to be reduced. That's what Boyle's law stated. Maybe we can illustrate some example how the Boyle's law can be applied. Let's say that you have a volume of 10 pounds. Let's say you have volume of 10 liter, I'm sorry, and let's say if the pressure is 1 atm. And in order to prove that, instead of, if you want to double up the pressure, instead of 1 atm, if you like to make it 2 atm, okay, so P1 V1 equals to P2 V2, which means that P1 V1 stands for the volume 1. This is like V1 and this is like P1. So P1 V1 is like 10 times 1, and P2 V2, let's say if the pressure is twice, so V2 is going to be what? V2 is going to be 10 divided by 2, so that is V2, which is going to be 5 liter. 5 liter. So you can easily see from here that from 10 liter, it automatically comes to 5 liter. How come that happen? Because you double up the pressure. Remember, you start with 1 atm, you double up the pressure 2 tm, so the volume is going to be reduced by half. So this is a good indication that volume is inversely related with pressure. That's what we call it the Boyle's law. So the next law is Charles' law. What does Charles' law states that? Charles' law said that the volume of a fixed amount of gas at constant pressure is directly proportional to temperature. So Charles he was interested with the relationship between volume versus temperature. So his theory was that if you increase the temperature, the volume is also increased. So it's not indirectly proportional, this is directly proportional. You increase up the temperature, you increase up the volume. So that way, when we consider about the constant volume and temperature, V equals to K times T, where K considered as a constant, so K would be V over T. So volume 1 over T1 equals to volume 2 over T2. That's a constant volume. Okay, so here the relationship between volume and temperature can be observed by considering pressure constant. Pressure has to be constant. That's very important. And the number of moles has to be also constant. These four parameters are really very important for you to calculate the gas-related issues. Okay, you need to know which values are changing. If you know which values are changing, whether it is pressure or the number of moles or temperature, that way you can able to see what laws are you going to apply. Are you going to apply Boyle's law, Charles' law, or Avogadro's law? If you want to apply the Charles' law, for example, make sure that the pressure is constant and the number of moles are constant. If there is a change between volume and temperature, the only law that you should apply here is Charles' law. If there is a change between volume and pressure, then you make sure that this has something to do with the Boyle's law. So let's see some practical example if Charles' law can make sense. If you have a volume, let's say volume would be, I would say volume 1 would be 10 liter, and if you have a temperature 1 would be 273 Kelvin. Okay, Kelvin is the unit of temperature in the SI system, and we wanted to see that, let's say if I would like to double up the temperature from 273, if I would like to double up, that means I multiply 273 by 2, which gives me about 546, 546 Kelvin. And I would like to see the change of the volume. What would be the change of the volume? Is it going to be double or is it going to be half? Okay, so V1 T1 equals to V2 over T2, which is, in my case, V1 is 10 liter and T1 is 273 Kelvin. So V2, which I'm about to calculate that, and 546 Kelvin. So obviously V2 is going to be, in order to get V2, I have to multiply 10 by 546, which is like crisscross, and divided by 273. So that gives me about 20 liter. You see, it double up. You increase the temperature here from 273 to 546, the volume is 20 liters. So volume is directly proportional to temperature, which is increasing the volume, increasing temperature. So that's what Charles' law tells us. So the third law that we considered is Avogadro's law. Well, what does Avogadro tell us? Avogadro is comparing, or Avogadro is interested that the relationship between the volume of a gas and the number of molecules of the gas. So according to his experiment, he observed that volume of a gas at a constant temperature and pressure is directly proportional to the number of moles of a gas. In other words, if you increase the number of moles of a gas, you increase the volume of the pressure. Now, one thing that I would like to tell you, at a standard temperature and pressure, 1 mole of a gas is considered as 22.4 liters. This is like a constant value. In other words, if you have 1 mole of helium, may have a different weight or mass, maybe like it has 4.00 grams, or 1 mole of nitrogen would have like 28 grams, or 1 mole of oxygen, for example, will have like 32 grams. But in terms of volume, at a standard temperature and pressure, all these have 22.4 liter, because all of these can be measured as 1 mole. So that's one thing that we need to pay attention. So basically, when we wanted to see how the Avogadro's law can be applied, volume is directly proportional to the number of moles, so we can somehow deduce these into a constant volume, which is volume equals to K times N. In other words, K would be V over N. If you can interpret what is K here, same as we did for Charles' law and Boyle's law. So we can see how the ratio of volume and the number of moles would give us a constant value. So let me start, say for example, if I have V1 N1 has to be equals to V2 N2, which should be a K value. If I consider my volume 1 would be like 1 liter, okay, and the number of moles of volume 1 will be the Avogadro's number. By the way, the Avogadro's number is also a constant number. 1 mole of any particle has 6.02 times 10 to the power of 23 particles or molecules or atoms. That's equals to 1 mole. Just think about that. If you go to the store and you want to buy 1 dozen of egg, 1 dozen of egg has 12 eggs. So chemists also measured 1 mole of a substance has 6.02 times 10 to the power of 23 particles. Actually, this number was first observed by Avogadro, so this is called the Avogadro's number. So if I have a volume of 1 liter and the number of moles would be 6.02 times 10 to the power of 23, and I would like to know what would happen, what would be the volume if I double up the number of molecules. Let's say instead of 6.02 times 10 to the power of 23, if I would have 12.04 times 10 to the power of 23. I know the numbers are a little bit huge numbers. I don't want you to take your time more, but I can guarantee you that the volume will be double up. This will be 12 liter. So these values will be constant. So if you divide 1 liter divided by 6.02 or 2 liter divided by 12.00423, you would get the same number. So this is one of the indications that the K value is constant. When you do the ratio of volume versus the number of moles, it always gives you a constant value. Now, we're going to come up with something called ideal gas equation. Now, what is the ideal gas equation is about? Now, the ideal gas equation is that so far we have seen that volume is inversely proportional to pressure. That was Boyle's law. And we also see that volume is directly proportional to temperature. That was Charles' law. We also notice that volume is directly proportional to the number of moles of a gas. That was Avogadro's law. So we're going to combine these 3 laws, and finally we have to come up with some kind of equation. That's what ideal gas equation is about. So the ideal gas equation is by combining the 3 laws. Volume is inversely proportional to pressure, volume is directly proportional to temperature, volume is directly proportional to the number of moles. So combining all these, we can come up with volume is proportional to the number of moles and temperature and pressure. Okay, if you have a huge number of molecules, you will have the volume will be higher. If the temperature is higher, the volume is higher. But if you have a higher pressure, the volume is going to be down. So this would give us a constant value. To make it equality, we use a constant of proportionality. We use that proportionality R. So we have something V equals to R NTP. Okay, so the R value is a constant of proportionality. The R value will be determined. I will tell you what would be the R value would be. So this R value will be given to you. It's going to be about 0.032106. I don't want to give you a wrong number. Actually, I don't remember on the top of my head at this point. But the R value would be a constant value. It's a numerical value. I have to say that. And this is called the ideal gas equation. The ideal gas equation. This can summarize all the Boyle's law, the Charles law, and the Avogadro's law. And next to that, we're going to do some practice actually to make it more clear for you. I would like to give you some examples. I also would like to calculate density of gases. It's also very important, density of gases. How do I do that? Actually, I can use the ideal gas equation. I like ideal gas equation because you can do so many calculations by using the ideal gas equation. So let's think about this. If we divide both sides of the ideal gas equation by volume and by RT, you can deduce this. You can say that you have PV equals to nRT. We can somehow write these as N over V equals to P over RT. They both are the same. If you crisscross them, you'll get the same number. I'm just rearranging this, but for a purpose. N over V is the number of moles divided by the volume. And as you know, moles times molecular mass will give us the mass of the object. So if you have N times M, which is a molecular mass, which gives you the mass of the substance, maybe I can use a big M to make it clear for you. I can use N times a big M, which is a molecular mass of the gas, gives you the mass of substance. In other words, the number of moles. If you want to know the number of moles, for example, the number of moles from our chemistry 101 would be the mass of the gas, the given mass of the gas, divided by the molecular mass, right? Molecular mass. I don't have enough space here. I should write capital M here. So what I'm trying to say is that, so if you multiply both sides by the molecular mass, we may come up with here, maybe I can write down here, we may come up with the M over V equals to MP over RT. Okay, I'm multiplying both sides by the molecular mass. So now here is the thing, M over V. What does that tell you? M refers to mass, V refers to volume. So basically, if you have the ratio of mass over volume, it's density. So density of the gas can be calculated at the molecular mass of the gas times the pressure over R, which is a proportionally constant value. You don't have to remember this number. This number will be provided to you, times temperature. So we can see from here that the density of any gas. If you like to compare density of carbon dioxide versus density of oxygen, the density of the mass of the two gases will play a great role here. So carbon dioxide will have a higher density than oxygen. Simple reason, because molecular mass of carbon dioxide is carbon dioxide would be 12 plus 32. I believe it's like 44, right? The molecular mass of oxygen would be 32 grams. So it will have a higher density. It will have a higher density. That means carbon dioxide has a higher density than oxygen. And as you know, substances that have higher density can be like used as a blanket. They can cover the substance. Substances that have a low density would be sink. What do I say? I'm confusing you here. Substances that have a higher density, they will be sink down. Substances that have low density, they can be like a cover. So that's one of the reasons that a fire extinguisher, for example, used carbon dioxide as a fire extinguisher, because you know oxygen is one of the flammable things that can cause fire. So since carbon dioxide has a higher density, it can cover the oxygen, so it's like a blanket to remove the flammable parts. So the techniques, the idea of fire extinguishers that uses carbon dioxide, because carbon dioxide has higher density. So we can able to do a lot of calculations using these three ideal equations, but one of the things that you need to remember here is that what kind of law are you going to use? Are you use Boyle's law, Charles' law, Avogadro's law? What makes you think that you can use one of these laws? Always list out what was given to you. If volume and pressure are given and the number of moles and the temperature are constant, then focus on Boyle's law. If volume and temperature are given and the number of moles and the pressure are constant, then use Charles' law. If volume and the number of moles were given and temperature and pressure are remaining constant, then you have to focus with the Avogadro's law. If the three of them are given, then if three values are given, three parameters are given, then you have to think about ideal gas equation. If the molecular mass is involving in the problem, then you have to deal with density. Okay. So remembering the laws and the principles would help you to resolve the problem. So I would suggest first, when you want to solve the problem, find out or identify what is known and identify what is actually looking for. That would be a big help to sort out the problems of ideal gas equations. It's not ideal gas equation, it's any equation that's related with gases. So I'm going to finish this video here. I hope you like this video. Please send me a comment in the comment section of the video, and I really appreciate all your comments. And if you have time, and watch it and share to your friends. Thank you very much, and I'll see you on the next video.